delighted to welcome Jen McGowan from Nature Matters, and also currently a visiting fellow at DICE through our E3 Sharing Space for Nature project. For the next three speakers, I will flag up when there's 3 minutes to go. So if you hear me saying 3 minutes, that's why. It's a great pleasure to hand over to Jen. So all yours, Jen. I can see your talk on the screen.
Great. Well, thank you so much for having me. And that was a brilliant presentation, I think, for me to follow with some of the messages I think will resonate well. I just want to acknowledge the collaborators. I'm going to be presenting on a variety of projects from around the world that this wonderful group of people in the Mark Sand leadership team have been working on through NGOs and universities over the last 5 years or so. But I want to just remind everyone at the moment of the challenge that we're facing. So the bending the curve on biodiversity loss, a lot of the history of systematic conservation planning has really been around establishing protected areas and classic area-based conservation. So OECMs is a newer trend in this, but we know that that's not going to really be enough. Adding more protected areas is not going to get us to full recovery. What we really need to be focusing on, in addition to growing our protected and conserved area estate, is looking at these production landscapes. And so how can we think about conservation and restoration and regeneration in these working lands and working oceans, because we need both of those things in order to meet our goals for mid-century. I think it's brilliant that this forum exists because this is a really important time for spatial planning around the world. This is from the task force, the IUCN task force on Target 1 for the Global Biodiversity Framework. And this is a global framework with lots of targets related to everything from restoration planning and urban greening to threatened species and sustainable development to mainstreaming biodiversity into every level of decision making. And what we argue is that Target 1, which is the integrated spatial planning target, that this is the foundational and enabling target to deliver on everything else. So spatial planning is so critical. Systematic conservation planning has a huge role to play. If done well, we can meet all of our targets and do it in a more efficient way. So why hasn't systematic conservation planning really been adopted? I will just borrow this slide, which I absolutely love. This is from here. And it really is, as Peter said, you know, the name of the game is space. We are all competing for space. And this is not uncommon to what we see as spatial planners around the world. And so we're looking at maps like this, and we're trying to also figure out how to improve ecosystem services, climate adaptation and resilience. This doesn't even consider things like connectivity or other ecological principles that Peter was speaking about in building networks. And so historically, what we've done is we've tucked our conservation areas in these places where a lot of other people aren't, a lot of other industries aren't. And we can't really do that because we see, even as area grows and our conservation network expands, species are still declining. So it's that messy bit in the middle where we need to be creating and working alongside production, infrastructure, and other uses on our land. So MarkSan is a decision support tool that has been used for decades around the world. What it does is it tries to meet goals that people set, targets that people set for nature or species or services or energy production even. And it tries to do that while minimizing the costs or the resources it might take to deliver on these plans, or really annoy as few people as possible. This is a globally trusted, many studies from around the world, peer-reviewed spatial planning tool that really directly aligns with targets 1, 2, and 3, or any type of area-based target that you might have. and it's informed conservation planning in over 180 countries. It sits at the heart of these inclusive and collaborative processes, and in doing that, we have a beautiful collaborative global community who works to support and build capacity in governments and NGOs and community groups all over the world. So what has MarkSAN done? It can be applied to all kinds of challenges. It can traditionally help build protected area estates, inform where OECMs could go, integrate things like KBAs into national networks. Multifunctional land uses and seascapes is a really important use for MarkSAN that continues to grow because we are increasingly working in multifunctional landscapes. The challenges are getting more complicated. Smart development planning, so infrastructure, mining and minerals planning, anything where you have a footprint-based industry where there are mitigation hierarchy or impacts that need to be addressed or offset, natural climate solutions, carbon farming. I mean, we haven't really gone into the nature market space yet, but I'm sure someone is thinking about how to use MarkSAN in that capacity as well. So all to say, a very flexible tool. I'm just going to speak to a few of these. This is by no means comprehensive, but these are just some of the examples that my collaborators and I have worked on more recently from around the world, which could be interesting. This is a nice example from the Midwest of the United States. This is the Quinoa Heartlands. This is an area that is a timber production area, but also has some of the last remaining spots of white pine, old growth white pine and spruce forests in this area. Ecological and cultural values are really important. And so what MarkSAN can help do is, as a tool that sits at the heart of these systematic conservation planning processes, is that it can build iterative models that incorporate, with a scientific heart, incorporate community feedback and community objectives. And so we can run scenarios to look at different management areas. This one is really looking at how can we build a management plan in this peninsula that is adaptive for future management. So timber production sitting along conservation. This is a marine spatial plan that emerged as basically in the procedure of the sovereign debt restructuring that happened in Barbados. This was a $150 million debt restructuring led by the Nature Conservancy and other partners. Barbados at the time was sitting at 0.1% marine protection, and as part of the goal, and this is happening around the world linked to other transactions that are similar, where countries need to bolster up their ocean protection to get to that 30% goal linked to a debt swap. MarkSAN is sitting at the heart of some of these. And so this is a zoning plan that's thinking about conservation, energy, fisheries, transport, tourism. So it's not to say MarkSAN historically has worked on a lot of protected areas. It is increasingly future directions-wise looking at these integrated multifunctional areas. The beautiful thing about this is it is very much around stakeholder collaboration. Equity and coordinated planning in the planning process is one of the most key elements to success. We can have the best data and the best tools in the world, but if we don't have buy-in from local communities at all levels and government, we're not going to be very successful. So another great example of this, Tanzania, which is one of the countries whose Ministry of Environment has really championed Target 1, really believes in the value of Target 1, that biodiversity inclusive spatial planning underpinning all the planning for the country. And this was around some work that the Nature Conservancy did with local communities on fisheries replenishment zones. So these are, it's a local managed procedure where they might temporarily stop harvesting in order to let these coastal fisheries recover. And so they wanted to work on an expansion plan for that, bridging traditional ecological knowledge with very sophisticated remote sensing and benthic surveys, integrate all different types of data and all different types of formats to come up with these community plans. I like this example because sometimes the outcome, yes, is always a map or a plan in the end, but the process is sometimes the outcome as well. And this is a lovely community, indigenous-led community zoning plan that was done in Australia, where the community was mapping environmental and cultural values, bringing together stakeholders in an attempt to create different scenarios to reduce potential conflict. And in the end, really, this is a great model for an inclusive participatory process that can be replicated and scaled where other Indigenous managed and community managed processes will be leading the way rather than it coming top down. Mongolia, I'm sorry, I'm just looking at time. I think I'm probably pretty close to being at time. Mongolia was one of the first countries to really jump in on 30 by 30. This is an example where we looked at systematic conservation planning, the largest remaining tracts of temperate grasslands in the world, which are disappearing fast. Big oil and gas exploration coupled with traditional pastoralism. And so we were able to use Marxen there on a national plan. Gabon, this is a freshwater plan. They're looking at where they can look at renewables, potential hydropower. 30 by 30 by 3 is Gabon's claim to fame. So they really want 30% of their land, freshwater, and oceans in some form of conservation by 2030. And the Okavango, really complicated seasonal dynamics. We have communities, we have tourism, and we are looking at energy security there. So all to say, we've learned a lot in these projects over the last 30 years. Aspects of success always come back to the early and ongoing stakeholder engagement, because we are shaping the plan, right? It's not the tools that shape the plan. It's not the data that shape the plan. It's the people. It's the goals and the vision and the future forecasting of what people want their lives to be and what nature can be. So it's not just one-off, it's also adaptive, making sure that iterative planning is a part of the process, helps address changing priorities over time, because people change, companies change, landscapes change. But empowering and in an engaging and inclusive way is really important. Obviously, around the world, Indigenous people and local communities have not always been included, and they need to be and are increasingly from many of these examples. So I think I will just end by saying where we're going is trying to build tools that are a bit more accessible and user-friendly, particularly for decision makers and non-experts. Marxen, why it is successful is because it does create that transparency in the science-based decisions. And finally, we want to scale systematic conservation planning around the world, and we are increasingly looking at ways to do that, not just through technology, but also through advancing the field. And one of the things I'm most excited to be working with Bob and the team at DICE on is how do we start thinking about integrating financial mechanisms into the landscape and also the socioeconomic impacts of some of these plans. And so I will just wrap there and say thank you. And that was a bit of a whirlwind trip of conservation planning around the world.
Fantastic. Thank you, Jen. That was brilliant. Yeah, as you say, a lovely tour around the world of all the different ways that systematic conservation planning and Marxen in particular has been used. So that's, yeah, as I said before, yeah, the joy of this community is there's a whole set of expertise internationally, and yeah, bringing that together to help inform what's happening in England is great. So thank you very much. Right, over to Fabrice. So welcome. So Fabrice from Newcastle University and the IUCN World Commission on Protected Areas. Really looking forward to hearing your talk. So please go ahead.
As Bob said, my name is Fabrice Stephensen, and I'm based at Newcastle University, and I'm also the Vice Chair for the IUCN World Commission on Protected Areas, specifically for the marine theme. So hopefully you can see my slides now. I can't see anybody. Yes. That's great. Okay. So this presentation is going to be marine focused. I'm a marine ecologist. It's going to be a single case study, and it's going to be talking about some of the work that I've been involved with colleagues in New Zealand. I'm going to talk through some of the modeling work that we did, but it'll be quite high level to just give you an overview of how we collated some of the data that formed our biodiversity estimates for conservation planning. And then I'll talk a bit about how that's currently being used and hopefully being implemented in the not too distant future. So this is just a bit of an overview about biodiversity models. It seems like everybody on this call will be familiar with it, but I just want to point out that getting spatial data for marine systems is really tricky. I would say maybe more tricky than terrestrial systems, just because of the difficulty in going to some of these places and the cost of going to some of these places. So we tend to use statistical or modeling approaches to fill that gap in order for us to get these spatial estimates of biodiversity. If you're familiar with species distribution models, that's more or less the approach that we used, although in this case, we're doing a community model. So we're estimating multiple species at the same time, trying to understand how those communities are distributed through space. So I won't go into the technical detail, but this is just a bit of an overview to say that we had lots of data, so 40,000 unique locations where we covered just over 1,700 taxa that live on or close to the seafloor. So this is a seafloor community classification. So that's organisms like macroalgae, demersal and reef fish, and also subtidal invertebrates. And we use all this data in a model called gradient forest models, which is a multivariate extension to a pretty popular machine learning approach called random forests. It's not particularly important. What's important is the output, which is the map that you can see there. This estimates species turnover. So that's the changes in species assemblages over space. And this map basically indicates parts of New Zealand. New Zealand's the fourth, between the fourth and the sixth largest EEZ in the world, depending on how you count overseas territories. But it's a very large marine domain, just over 4 million square kilometers. And across this area, which is the study area, we estimated these species assemblages. So the colors represent similarity in these assemblages. So where you have similar colors, you have similar assemblages. So for example, if we look at the Campbell Plateau, which is down in the south, I hope you can see my mouse, but if not, it's the south of the study area. It's got all these pinky colors, and at similar depths on a similar kind of plateau up in the north, and the Challenger Plateau, you still get very different assemblages. So that's what we're doing. We're mapping these species turnover. And what we can do with that is we can combine that with richness, and through a classification approach, estimate how we can group these into communities. So that's what we did here. This map now shows 75 individual groups that have been grouped together based on their similarity in assemblages and environment, and also richness and aspects of endemism. For some of you working in Europe, you might be familiar with the UNIS classification. This is a very similar approach in the sense that we want to group things together, give them a name, and be able to describe the kind of characteristic species within that group. But it's a little different in that it uses a model to predict those classes, and therefore allows us to map these areas spatially. We can also use this classification at different scales. So we can think about these areas at a bioregional scale, and combine these two kind of layers, give us a lot of information for conservation planning. There's a couple of QR codes in the various slides. That's links to the papers where there's a lot more kind of technical detail if you're interested in the approaches. So this work was funded by the Department of Conservation, the New Zealand Department of Conservation, and they presented this work to stakeholders and ministers. And one of the first things that came back was that they wanted to understand how well this model was working. So there was a level of uncertainty associated with using kind of model outputs for decision making. So the first thing that we did was to test how well this model worked. So a couple of years later, we had enough independent data to test the model completely. So we had just over 4,000 trawl samples that sampled the demersal fish assemblages, and we had over 700 benthic toes with video camera to estimate benthic invertebrate assemblages. And we just wanted to see how well these samples, when split into the groups, were able to kind of show differences in the groups. So again, there's a whole load of technical stuff in here, but I'll just pull out the main finding, which is that between our 75 groups, they differed from each other, which is good. and the model was able to discriminate those groups very well. And the underlying data of the groups are these species compositional, or the turnover in species turnover rather. And we're able to then look at the observed compositional turnover from our samples compared to our predicted turnover. And there were some reasonable relationships between those. So that gave the government in New Zealand confidence to say that there was some maps of biodiversity and that they could start to be used to think about how well some of the spatial management areas in New Zealand were doing in terms of their representativity and various other measures. So the first thing they wanted to do was to look at reporting. So we overlapped the spatial management areas in New Zealand with the Seafloor community classification. And we wanted to look at the extent of each of the groups and the proportion of each of the groups within these areas. And that was used for reporting towards kind of international biodiversity commitments for the Global Biodiversity Framework. So there's a map there on the right. So the spatial management areas cover approximately 28.5% of the marine domain. But I would just say that these are definitely not all MPAs. The little red sections that you might be able to see in the map, those are the Department of Conservation marine reserves. Those are definitely marine protected areas, whereas the other colors that you see on the map wouldn't meet the criteria, I think, most of them, for being classified as marine protected areas. But nevertheless, they do provide some management measures in place that would mitigate impacts to seafloor communities. So given we're talking about, in this case, thinking about seafloor biodiversity, it's a useful way of thinking about current protection measures. So as I mentioned, the first thing we did was to look at the extent and proportion of the groups within these management areas. And the first takeaway was that some groups are very underrepresented. So 25 groups out of the 75 had either very small areas that overlapped with the current protection or very small percentages of their overall extent. So we classified those as underrepresented. But more importantly, some of these groups are not represented at all. So 21 out of 75 groups don't overlap at all with any of the current spatial management areas. So as you might have noticed from the previous map, a lot of these spatial management areas are offshore. So there was these large extents of offshore protection, which cover the deeper water groups from our classification. But the highest amount of biodiversity in the marine environment is that coastal zone. The transition from the high water mark through to approximately 200 meters of depth is where we'll get the most difference in our species, the most diversity, where we have that highest species turnover across the shortest kind of distance. So the map here on the right shows us some of the groups that are either absent, so that's the red bits, or severely underrepresented, which are these orange bits. And so all of these are in the inshore. Coming back to Peter Brotherton's point there about kind of the importance of high quality protected areas. The New Zealand marine reserves are inshore and cover some form of, well, overlap in some way with 47 groups out of the 75. So they obviously cover, sorry, can't seem to get rid of this notification. Oh, there we go. So they cover a lot of the inshore and they cover a lot of the groups that we had information for, but they only represent 0.4% of the EEZ. So even though they overlap with a lot of the different groups, they don't overlap with lots of them. So they're still kind of these underrepresented inshore groups. So based on this data, so we've done some reporting with it, and then the next step is really just to think, you know, if we accept that the seafloor community classification represents seafloor communities, and we accept the principle of representativity that we should try and protect, you know, important parts of each of the groups, that we represent all aspects of biodiversity, then the next question becomes, so given the current spatial management areas, where would we want to go to next if we wanted to explore filling in some of the gaps that currently exist within the spatial management measures? So we did a spatial prioritization analysis in a software called Zonation, which is very similar to Marxan in many ways. And the data that we used within it is quite particular, and it's kind of quite a big step forward in many ways compared to other analyses with kind of classifications, because we had species turnover data spatially. So for each group, and this group represents some of the data that we had for group 20, which is a group that has lots of deep water corals, as well as lots of fish assemblages that are related to those habitats. So for each group, we have an estimate of within group similarity. So this shows how typical the kind of species mix is within the group. So these kind of reddish areas are places that are very representative of that kind of species community, and the cooler places are less typical. So we have an understanding of the quality within each group, and we can also understand how different that group is to all of the other parts of New Zealand. So that's the second map there, is the between group similarity. And this shows us how different this area is compared to other groups, where these warmer colors, the reds, represent very different species composition. So that allows us to start thinking about, if we want to prioritize certain areas, how do they complement each other, or how unique are they? We also obviously have estimates of richness, and we've clipped it out there just for group 20. This is just the demersal fish richness estimates, but it basically just shows that within a group, not all parts of that space have the same value in terms of species richness. So again, the warmer parts are the places that have high richness. And based on my own knowledge, where you can see those little slivers of red in there, those are associated with deep water coral reefs with very high productivity. Okay, so for each of our 75 groups, we have these different layers, and we put all these layers into a spatial prioritization to give us an idea of where we might want to go to next if we want to expand the current spatial management areas. And this is what the map looks like, the outcome of the spatial prioritization. The red areas represent our current spatial management areas, and then areas that are brown represent the next 1.5%. So remember, I said that the current spatial management areas are 28.5%. So in this scenario, we're thinking, if these are all counted towards the Global Biodiversity Framework Target 3, and we wanted to add 1.5% to meet the 30 by 30 target, where would we want to prioritize our efforts? So that's the brown sections. And then the pink represent an additional 5% on that, and the yellow an additional 5%. So kind of in increments, we could think about how much more area we could add to our spatial management areas, and what value that would give us in terms of biodiversity. So first of all, just to look at the overlap with our current areas, so that's the 28.5%. I've only pulled out a couple of metrics, and this within group similarity metric is kind of tricky, but this is a low percentage basically, which means that it captures relatively unrepresentative areas for each group, and it will definitely not capture all the species and communities across the study area. So 11.65% on average, and in terms of all of the richness within New Zealand, it was only capturing 8.75%, so very low. So when we look to expand that by 1.5%, which are these brown bits in this map, I've kind of pulled them out so that you can see mainly that they're just very small areas and that they're all inshore. So if we added that 1.5% of areas to our current spatial management, we'd get this huge gain in terms of biodiversity value. So a really small strategic addition to a network could increase the within group similarity to an average of just over 55%, which is a really large increase, and capture almost 60% of species, the total species richness within New Zealand. So although that's not necessarily the full amount that we consider adequate, that's maybe a decision that rests with policymakers. I think what this does highlight is that with these kind of strategic actions, we can get really big gains, especially if we use maybe new or developed biodiversity estimates that aim to represent not just certain key species, but the range of biodiversity. So that's my talk. I just wanted to quickly acknowledge a lot of colleagues who have helped with this work. and also many who aren't there on the photographs who helped with previous iterations of environmental classifications. I'll quickly flash up the funders, in particular the Department of Conservation, the New Zealand Department of Conservation, that funded several of these projects. So thanks very much, and look forward to the rest of the talks. Thank you.
Fantastic. Thank you very much, Fabrice. I've been told that people can see me not looking at the screen, and I should explain that that's because I was making notes about the questions that I want to ask Fabrice in the session at the end. So yes, I hope everyone else is also writing down their questions for that later session. Brilliant. Yes, and it's really nice to have a great marine example like that, an example of another software approach too, just to show the breadth of the work that falls within systematic conservation planning. Right, so yes, I want to welcome Dr. Dominic Munsell from University of Kent, DICE, he's been the tech genius behind several of our projects here, and it's I think this is one of the most exciting ones, so it's brilliant that he's able to talk now. Over to you.
Great, thanks. So hello everyone, my name is Dominic Munsell. Currently I'm a postdoctoral research associate at the University of Leeds, but I just finished working at DICE. So the project that I'm talking to you about is some work that we did at DICE over the past 3 years. And it's about looking at spatial prioritization for conservation, restoration, and poverty alleviation in Indonesia. So this work was from a Darwin Initiative project, which involved DICE and a number of partners across the UK and across Indonesia. So the UK Centre for Ecology and Hydrology, Plan Vivo, Fauna and Flora, KKI Varsity, and Universitas Indonesia. The project was about developing an evidence-based approach to forest restoration, figuring out where to restore, how to restore, and how to monitor outcomes, and then how to link restoration to certification for ecosystem service-based finance. And our work was focused primarily in the two provinces of Aceh and Bengkulu on the Indonesian island of Sumatra. So globally, forest restoration is recognized as a key tool for carbon removal and biodiversity conservation. And here's a paper from 2020, which found that nearly 300 million people live on tropical forest restoration opportunity land in the global south. So that forest restoration that prioritizes local communities is a promising option for aligning global agendas for climate mitigation, conservation, environmental justice, and sustainable development. And this also neatly aligns with the expansion of OECMs and PAs under the 30 by 30 targets and the UN Decade of Restoration. So to give a bit of context and background for Indonesia, historically, the forests have mainly been managed top-down, so through central government control. But then in 2014, the government of Indonesia launched a program to allocate 12.7 million hectares, or roughly 13% of the total forest land, to local communities, basically giving local communities forest management rights by 2030. And the stated goals of this program are social, economic, and environmental. So quite a lot of things that they're trying to achieve. They're trying to alleviate poverty and develop sustainable livelihoods, halt deforestation, end forest conflicts between different users, and protect and restore biodiversity and ecosystem services. The social forestry program, there's a range of different schemes like village forests, community forests, forestry partnership schemes, and they're all slightly different as to what the specific management objectives are. For example, some might be about watershed protection, or some might be more focused on livelihood development. So under a previous Darwin project in 2019, there was actually an evaluation of some social forestry schemes in the island of Kalimantan. And so they used statistical matching and found that indeed there is a detectable reduction in deforestation and improvement in well-being, as you can see from these graphs at the top, A and C, although this was dependent, not in every case, so this was dependent on the land use zone and the type of the scheme that was implemented. And then interestingly, they also found that there were often trade-offs between objectives. So you couldn't, only in 51% of cases was there both a reduction in deforestation and an increase in well-being. Whereas in other situations, sometimes there was a negligible effect in one and a positive in the other, or a trade-off, so a negative in one and positive in the other, or negative in both. So where we came in is, so by 2022, around 5 million hectares had been licensed. So 5 million hectares of land had already had social forestry schemes in place. As you can see, those are the purple bars in the chart. And you can see there's quite a strong east-west gradient. So there's a lot more schemes that are operating in the west of the country, in Sumatra and in Kalimantan than the east. And this is consistent with a wider east-west gradient in conservation spending across Indonesia, where the western part of the country has historically attracted much more investment and much more institutional presence. But you can see, if you look at the size of the black bars, which is the area of land that's eligible but not yet licensed, there's quite a lot of potential for additional land to be allocated. So our question was, given that there is still so much land left to be allocated, how can we perform a spatial planning or spatial prioritization to help guide future social forestry implementation? And I should say that not all forest land is eligible for social forestry. The government actually publishes a data set which it updates periodically on, and it basically says which areas would be theoretically eligible. So we developed a spatial decision support tool with the goal to identify areas of importance for social forestry with these three objectives: to protect biodiversity while maximizing forest restoration and alleviating poverty. So we had a bit of an introduction to SCP by Bob in the beginning. So we used a thing, R package called Prioritizer, which functionally is very similar to Marksan. So we covered the region in a hexagonal planning unit grid, which covered existing protected areas, shown here in green, areas that already have social forestry implemented, shown here in purple, and then these eligible areas, shown in white. And we first performed a gap analysis. So a gap analysis was basically to determine how well each of these three objectives was already captured by the existing protected areas and existing social forestry schemes. And then we ran the prioritization, which was basically running an algorithm to pick additional planning units and assess which ones will give you the biggest gain for each objective for the least amount of cost. So to represent our first objective of protecting biodiversity, we used two data sets, which some of you might be familiar with, at least one of them. So one was the global IUCN and BirdLife species range maps, and we limited that to species classified as vulnerable or above. And the second was a national land system classification published a while back in 1990, which divides all of Indonesia into different land or habitat types according to soil and habitat, which you can see here down here, 18 different types. And so by combining these two data sets, we were aiming to achieve a comprehensive and representative coverage of biodiversity. And the benefits of all of the data sets that we used were available at a national scale, which was a requirement since we needed to use the same data set for all of our analyses. For our second objective of alleviating poverty, we represented poverty using a multi-dimensional poverty index published by Courtney Morgans, who was also based at DICE. It's based on 15 indicators, so across these five categories of education, health, living standards, infrastructure and services, and social cohesion. So villages score either a 0 or a 1 for each of those individual indicators. So the highest possible score a village could get is 15, in which case it would be the most deprived or have the highest level of poverty. And this data set is based off of a village level census conducted by the National Statistics Agency roughly every 3 years. And because it's village level, it's quite high definition, like quite high resolution data that we have. And then for our third objective of representing potential for forest biomass restoration, we used a global satellite imagery 1 kilometer square data set of forest above ground biomass. So we limited analysis to just undisturbed or degraded tropical moist forest, and then stratified the landscape by lowland, wetland, upland, or montane, and then calculated potential as the difference between the maximum biomass in a given province, in a given landform, to the measured biomass in a given raster cell or location. And we also had a lower threshold of if forest biomass was below 74 tons per hectare, which is classified as scrubland, we said don't prioritize that because it has the cost of restoration is prohibitive, and the chance of restoration success is also is low. So in the illustration on the right, you can see that in Sumatra, biomass ranges from 0 to 591. So the higher priority would be the location that has, say, 300, which is medium range, rather than the location which has 500, which is close to the upper limit. So we had our 3 objectives, and then we had all of our data sets which reflected or represented those objectives. We processed them using GIS, and then we plugged them into the R package prioritizer. Some other parameters that we played around with was weighting of different objectives, which I'll go into more detail in a moment, and also spatial clustering of solutions. So spatial clustering is quite a common practice, and it basically helps produce connected contiguous priority areas that are often more ecologically effective and also easier to manage in practice. So we plugged all that in, and then at the end we had maps of priority areas that we could share with stakeholders. So a bit more detail about the spatial prioritization. So quite a large area, since this was for the entire country of Indonesia, we had 497,000 hexagons. Each was 100 hectares in size. So those were our planning units across 28 provinces. For each of those planning units, we calculated how much of each data set or conservation feature was contained within. So how many species, how many land types, how much carbon. And then we ran the algorithm to select the 10% of best hexagons that satisfied each of those objectives. And then we repeated that in increasing 10% increments. So 20%, 30%, etc., all the way to 100%. With the resulting output being what you see on the right. So on the right is basically the solution or the output, the result of that analysis, where you can see that the hexagons are ranked from red being the highest priority at 10 to blue at 100, where it's the lowest priority. And then the gap analysis, the existing areas are shown by green and purple. So in terms of cost, we used just the area of each planning unit as the cost. So these rankings can also be interpreted as an area percentage. So 10 would be if selecting 10% of the area, 10 is selecting 20%, etc. And at 100, you're selecting 100%. So yeah, we also explored alternative objective weightings. So the reason we did that was to give us more flexibility to engage with decision makers. And this is a parameter that we manipulated in the algorithm. So the different weightings can reveal the sensitivity of prioritization outcomes to policy preferences, and they can also help identify robust priority areas that might not change despite changing the weightings. And they can also help tailor different funding streams to different places. So for example, funders can target climate finance in restoration-rich areas, and they can target social funding where poverty benefits dominate. So the figure on the left shows a Pareto frontier. Each circle, each of those blue circles, is an individual solution for which we could create a map, as that I showed you in the previous slide. So each of those circles could be turned into a map. And when we have an equal weighting, there's a balance in the amount of total poverty on the y-axis and the amount of restoration, forest restoration on the x-axis. Whereas if you increase the weighting for restoration, you can see that the solution moves down to the right. So you can have more forest biomass restoration at a cost of reduction in total poverty score. And on the other side, you can increase the weighting for poverty, but then that comes at a trade-off of reduced achievement of the forest objective. So each of those Pareto frontiers, if you look at the figure on the right, there's 9 Pareto frontiers corresponding to each of those 10% increments. And so the two axes tell you how much of each of your two objectives you're achieving. And then the third objective of the species protection or the biodiversity protection is captured by that color scheme going from brown to blue. And so once we had our outputs, we decided it would be a neat idea to maybe share or put our output maps, our solution maps, on a Shiny app. So for those of you that don't know, Shiny is also an R package that you can create an app that can then be uploaded to a website, which means that anyone who just has access to a web browser on their phone or on their laptop or on their tablet can just go to the website and then look at this interactive map, zoom in, zoom out to their specific location and see how their area that they're interested in comes out with this prioritization analysis. So down here is the link if you're interested in looking at that, or that QR code will also take you to it. And so, yeah, we just thought this is a nice way to make it a bit more easy for stakeholders to engage with the results that we come up with. Yeah, thank you very much for listening, and I'll be happy to be taking your questions later on.
Fantastic. Yeah, no, that was great, Dom. Really nice explanation of a quite complicated thing. And yeah, bringing together all those factors. And again, I think a nice illustration of, so another software package and another very different context and accounting for lots of different factors. So yeah, that was a brilliant example together with the other two talks to sort of showcase the range of different ways that everything can be used. So thank you very much.